Good afternoon. We are Team 23094 working on the Biomedical Sensor Board, or as we like to call it, the birthday cake. This project is sponsored by the University of Arizona Department of Biomedical Engineering. Before we delve into the intricacies of this project, we would like to introduce you to our team. Meg Guile is a biomedical engineer right in the middle there. Tony Colong is an electrical and computer engineer right over there on the left. Barbara Bruno is a biosystems engineer, second from the right. Diana Picone is our procurement lead and a biosystems engineer, second from the left. And Riley Watson is our team lead and a biomedical engineer, all the way on the right. Our project is based upon creating a Raspberry Pi hat that will interface with the GPIO pins on the computer and integrate 5 different biomedical sensors. These sensors are electrocardiogram, bioimpedance, pulse oxygenation, a microphone, and temperature sensors. The system is designed to be used for educational purposes, such as the various biomedical engineering laboratories that undergraduates will face. Here's just an example image of our Raspberry Pi hat sitting on the GPIO pins. It provides a visual reference for our end goal and why we have chosen to call our project the birthday cake.
Due to the nature of our project, given the physical constraints of the Raspberry Pi, our approach is straightforward. We must research the physiological signal for better understanding of it, pick the sensor and components required to support it, analyze datasheets to ensure functionality with the Raspberry Pi, create circuit diagrams, manufacture and assemble said circuits, create custom code drivers in a GUI, then test and diagnose our board as necessary. Our sponsor has defined our system with 23 system requirements. Not all are covered in this video, but the main ones surround sensor accuracy, medical device standards, privacy protection, cost, and ease of use. It is worth noting that there are sensors such as the ECG and pulse ox that have been known to work with the Raspberry Pi and are mass-produced by companies such as Adafruit. However, we believe that simply copying their design would not highlight our engineering capabilities, so we have opted to use sensors that have not been integrated with the Raspberry Pi before. Since a lot of our project is based conceptually around the sensors we chose to utilize, we can complete an initial analysis of our design through looking through manufacturer datasheets. This example shows that our temperature sensor will be within our required tolerance of 1 degree Celsius. This has been completed for all of our sensors to ensure accuracy and that they are capable of being powered off of the Raspberry Pi.
Of uttermost importance to our project is safety. We need to ensure the devices we choose will not harm the user in any way. It is particularly evident to the bioimpedance sensor as you are injecting an alternating current into the user. This is defined by the IEC 6061-1, which states the maximum AC voltage that you can inject as a function of frequency. This is a very simplified overview of the system, but highlights how we will comply with the standard. We will get into the modeling side of our project, which is taking the components that we have selected and verified and creating circuit designs for them that will interface with the Raspberry Pi. We will then take this and create custom PCB boards within all Eagle CAD. Another large system requirement was to ensure that our hats fit within the physical footprint of the Raspberry Pi. So we created an outline of the Raspberry Pi hat in Eagle before embedding our circuit designs into them. In this image, you can see the pulse ox circuit and the outline of the Raspberry Pi hat that will then be sent into manufacturing in slide 12. Here are the rest of the circuit designs. Each design was then sent out for manufacturing to JLCPCB. They simply created the boards we had designed and sent them back to us for manufacturing. This was done as the PCB mill within the solder lab was not available to us.
Once the board were received, we then get into assembly of the board. This was done using the SMD working station in the solder lab, and each one was hand soldered. Here is a video of Riley soldering one of the board, and then a video of the final product. All the 0603 in this way soldered with solder paste and a heat gun, while the female headers were soldered using the traditional solder wire and a solder iron. All the board will be manufactured, we began to focus on the code design. The main problem that presented itself was that none of these chips have been coded in Python, only either in C++ or Arduino IDE. So we had to create custom drivers for the sensor in Python. For I2C communication, we choose the SMBus library. For I2S communication, we choose the Pi audio library. And for SPI communication, we choose the SPI dev. Here is an example of the code we wrote to control our AD593-3 power impedance microcontroller. And here is a video of our GUI. So we then are asked to create a GUI for the user. This was done using Python Tinker, as it was a backend of the matplotlib library that allows for graphing of data. The user will see a home screen and can then select the sensor that they would like to use. The GUI is also coded to test for the device to see if it's connected and raise an error if it's not. The buttons are all variable locked, so only one sensor can be used at a time to reduce the overhead of our code. And here we can see the microphone picking up sounds, followed by the bioimpedance sensor, taking impedance measurements, and finally the temperature sensor on our GUI.
When we get into the results, we have discovered that currently we have 3 of the 5 sensors working as intended and fully custom driven in Python, as well as GUI or GUI. These sensors are the microphone, bioimpedance, and temperature. The current issue we're running into related to the circuit design and SPI communication. In reviewing the circuit design, we found that there were some contact errors which led to shorts in the circuit. We also have not been able to use SPI dev library to confirm communication with the device as of yet. This is the biggest issue we have run into, but there were other along the way. Here are the verification requirements that we went throughout the entire process. Feel free to pause the video at any point and reach out to us with any questions regarding the tests or methodologies that we went through. Along the way, we faced various challenges we had to overcome. These included, or not limited to, limited team experience with the SMD soldering, no experience utilizing Python packaging, SMBus or SPI dev, SPI communication issues with the ECG or pulse ox, and PCB design inaccuracies in the GPIO connections and choices. We learned various important lessons in the engineering process, such as the importance of project time management, asking for help from experts in the field, and double-checking our tolerance before sending the prototypes into manufacturing.
Overall, our deliverables to our sponsor include 5 separate PCB hats with a self-contained sensor, a GUI that is executable from a desktop icon, and a user manual that explains the physiological signal and how to use our devices. We would like to thank the University of Arizona Biomedical Engineering Department for creating this project for us, and we look forward to the way the Biomedical Sensor Board can be utilized in the future.